do this. So x comma d and x comma d prime are same as topological spaces because the local behavior around each point is the same for whatever these d or d prime you have chosen. But we want to make sense of the large scale aspects, like what's happening outside the ball one. Then this language is not enough. So then you have a different collection of subsets to consider to make sense of that language.
Oh, okay.
So that is what known as coarse structure. So coarse structure basically talks about the large scale aspects of the geometry of the space. So given x comma d a metric space, you can consider the set x cross x. That is the Cartesian product. So this is x comma y, x belonging to x, y belonging to x. So, a natural way, like I was talking, we have to consider again collection of subsets. So coarse structure will be a collection of subsets. Coarse structure is a certain collection of subsets. Is again collection within inverted commas. Sajid showed me today how to get this trick done when you don't want to say a lot about it, but I'm just making it, highlighting it here. Coarse structure is collection of subsets of x cross x that makes some sense, that follows some idea, like it should also follow some separate axioms. Follows some axioms. So you have already the information D, the metric on the space X. So a natural thing to consider would be this kind of subsets of x cross x. X comma y such that distance between x comma y is less than equal to k. Now you see, last time you had balls, which was balls around a point x. Now it's a different thing. Don't get confused by this less than equal to. So I might make you confused and use r instead of k, where r is some positive real number. So, but this is very different from what we were doing there. We were considering collection of balls around x. So what we are doing here is, if you say map x this side, this is for pictorial representation. Of course, no one can think of like very little about this. So this would be all points on this line will be x comma x, right? Where x belongs to x. And what we have done here is kind of consider a tube around this diagonal. So this length is r.
So D is defined like that, or D is defined like that, or
No, you're using D to define ER.
okay.
ER is this set, this tube around the diagonal. That is ER. This is a very natural thing to do. I mean, once you are trying to consider subsets of x cross x, and you have the metric information, this is the first thing to look at. But that's how they looked at or not, I don't know. But I'm saying like it's very natural, comes from the. So you're using this metric definition to define a subset of x cross x. So our point is to define a subset of x cross x.
Okay.
And we have the information of the metric. So the most natural choice is this. I mean, what else could you have thought about? I mean, of course, you can think about a lot of things, but we have to make sense of the large scale aspects of the geometry. So this is how we can do that. I mean, we can start with this kind of subsets, this collection of subsets, which will again follow some axioms.
Some axioms.
I'm not coming to that. Yeah, so coming to axioms. So that would define a coarse structure. Once you have a collection of such subsets of x cross x, axioms for a coarse structure. Yes?
Instead of this carbon cylinder, if you like straight also it will obey this equation, right?
How will you write down? Okay, I want to work with it. So let's see.
The distance will be less than r, or
No.
distance between x and y can be less than r, right? Like,
So you are saying about this. This length is?
if you put any x, y, then it will be less than r. Maybe not same, but it will be.
So you take a point x1, comma x2.
So what was the question?
And the shape also obey that equation ER, right?
No, it won't. I mean, ER defines that. Like, so I'll show you how. So you have x1, comma x2 here. This distance that I was talking about, this is not a real plane, first of all. So what you have here, so how you can make of us, how you define such a strip? That would be the question, right? So what elements belong to this strip? So this will be the collection of all x1, comma x2 belonging to x cross x, such that
dx minus 2.
so this would be x1 here.
dx is too close to some x1
Or x and
or x2.
d should be less than.
I mean, first of all,
Zero.
what do you mean by this strip of length r? I mean, so it would mean that in x2 you can define a strip of length r, right? So in y variable you always have, so you have x1, comma x2 belongs to this strip. So I'm naming this strip as S. Then x1, comma y belongs to S if dx2, comma y is less than or equal to r, right?
The same.
That is what you are having.
xy less than is r, and now it is x2y less than r. Both are like same.
What? No, there we are taking all the collection of points x1, x2 such that distance between each, like x1 and x2 is less than or equal to r. Here you have collection of points. So this is how it will define S, right? In some sense. So if x1, comma x2 belongs to S, then x1, comma y belongs to S if dx2, comma y is less than or equal to r. There you had, this is a very different way, like this set is a very different set. This definition is required for that set. This is no more x, comma y such that dx, comma y is less than or equal to r. This condition here, that will only define that tubular neighborhood of radius r around the diagonal. You get that point here now? Oh, okay, I was talking about axioms for a coarse structure. So ER we have defined like this. This is a subset of x cross x. And you can consider all the collection of subsets r greater than 0. Right? This will be a collection of subsets of x cross x. So far, we have just defined this collection. Now we have to make sense of large scale geometry. So before going into the axioms for large scale geometry, I would like to say what do we mean by large scale geometry, right? I mean, so if you consider this space of integers, so you have the real line. So this is the real line. You have 0 here. You take 1, you take 2, 3, minus 1, dot dot dot, minus n, dot dot dot. So we are only taking the space of integers, z. Space of, so this is set of integers, if you like. So it will automatically have the topology coming from R as a subspace topology. But I haven't defined what do you mean by subspace topology and things like that. We are not working at the topological level, so we don't need that. Space of integers. So that would look like some dots separated by a distance 1. Like in the physical intuition space, like R3, if you fix one coordinate and you take the space of integers along that, you have just a space of dots as your space. So this is a set with some topology and things like that. Now you want to look at this space from a certain distance. So if you go far away, like if you look at a certain distance, so I'm standing here and it looks like the distance between them is 1. But when we try to define a notion of relative distance, like where I'm standing and looking at it, so a priori they have the distance 1, but to me, what we will see as I go far away, that they come closer together, right? And that's how you see mountains get bigger and bigger and things like that. So our perception is that is coming together. Now you try to think about what would happen if we try to see at the space of integers from infinity. So this distance will collapse completely if we go to infinity.
From which direction are we looking? Like what is there? It is another axis we are talking about.
Yeah. I'm looking from. I'm not staying here and going along the same direction.
Probably it will be the perpendicular axis, right?
No need of perpendicular. You're talking about the nature at infinity. So at infinity, there is nothing like you have to be, and this is an infinite space itself. I mean, how you define perpendicular? I mean.